A one-file llama.cpp patch reportedly made decoding about 1% faster on an AMD Strix Halo machine. No new model, no magical quantization, just a less wasteful way to copy rows. That sounds tiny, because it is, but this boring patch exposes the real engine of local AI. Thousands of low-level choices about memory, layouts, kernels, and hardware utilization. Release B100L076 describes a vectorized path for same-type get-rows operations. In plain English, eligible GPU threads can move a 16-byte chunk instead of copying one element at a time. Get-rows is exactly what the name suggests. Take selected rows from a tensor and place them somewhere else. Embedding lookups and recurrent-state operations can depend on this gathering step. This is not a glamorous matrix multiplication packed with arithmetic. It is largely data movement, so performance can depend less on raw compute and more on feeding memory efficiently. The previous kernel assigned roughly one element to each thread. It also repeated row invariant setup work, including index loading, division logic, and pointer calculation across those element copies. Imagine 16 delivery drivers independently checking the same address before carrying one envelope each. The envelopes move, but repeated preparation consumes instructions that do not improve the result. The patch moves that shared setup outside the per-element loop. Calculate the row information once, then let the loop focus on copying data. Compilers love clarity. GPUs love less bookkeeping. For the fast path, each thread copies an int4 value, 4 32-bit integers packed into 16 bytes. That turns several narrow memory operations into one wider transaction. Wider copies can reduce instruction overhead and better use the memory path. The math is unchanged, and the bytes are unchanged. The machine simply handles them in larger parcels. But vectorization is conditional, not a free turbo button. The release notes list compile time type checks and runtime requirements for alignment, row strides, and dimensions divisible by the vector width. First, source and destination types must match. If copying also requires conversion, raw 16-byte movement is not equivalent, so the specialized same-type route does not apply. Second, base pointers and row strides need 16-byte alignment. Hardware likes wide transactions lined up cleanly. Awkward boundaries may require extra accesses or make the operation unsafe. Third, the row width must divide evenly by the vector size. Otherwise, a wide copy loop needs tail handling, and this implementation chooses the established scalar path instead. There is another catch. Doing more work per thread means launching fewer blocks. For a small gather, that can leave GPU compute units idle and actually make vectorization slower. So the patch adds an occupancy gate. Large, suitable gathers use the vectorized kernel. Small gathers stay on the block-rich scalar kernel. Faster code sometimes means preserving the old code. On Strix Halo, the author reports a large DeltaNet recurrent-state gather falling from 18.6 to 13.0 microseconds. Across get rows in that test, time dropped 27%. Yet total decode speed reportedly improved only around 1%. That is Amdahl's law in everyday clothes. Accelerating one slice helps only according to how much runtime that slice consumed. If an operation occupies 4% of runtime and becomes roughly 1/4 faster, the total gain lands near 1%. Huge local improvement, modest system improvement. Both statements can be true. Do not convert that 1% into a universal expectation. The cited measurement targets Strix Halo, a particular backend path, and a workload containing the large gather this optimization favors. llama.cpp supports many backends, but their kernels are not interchangeable. CUDA-style source can target AMD through ROCm tooling, while Vulkan, Metal, CPU, and other paths need different optimizations. This is why the same model file can perform differently across applications. Runtime version, backend selection, kernel coverage, memory allocation, and scheduling all shape the tokens you actually receive. Quantization is not merely a smaller number on a download page. It changes how weights are grouped, packed, decoded, and consumed, which determines whether a backend has an efficient kernel. During token generation, many local models repeatedly stream weights from memory. When arithmetic units wait for data, buying more theoretical compute does little unless bandwidth and kernels can feed it. Prompt processing and token generation stress hardware differently. A patch improving a recurrent state gather during decode may move generation speed while barely changing how quickly the initial prompt is ingested. Architecture matters too. The highlighted benchmark involved a DeltaNet recurrent-state gather. A model that spends little or no time in that pattern cannot harvest the same improvement. Still, 1% is not meaningless. Runtime projects accumulate optimizations across matrix math, attention, sampling, memory copies, and scheduling. Enough honest 1% wins can become a noticeably better release. A small speedup can mean lower latency, slightly less energy per response, or more concurrent users on fixed hardware. At scale, boring efficiency work quietly pays rent every day. Optimization also needs guardrails. The release reports all 47 get-rows backend tests, passing, and the small convolution state gather avoided regression by retaining the scalar path when occupancy mattered. For builders, the lesson is simple. Benchmark the exact runtime, model, quantization, context, and backend you deploy. Someone else's chart is evidence, not a performance warranty. Record the commit or release tag, because llama.cpp changes quickly. Comparing an unnamed latest build against last month's package mixes kernel improvements with every other change that landed between them. Measure prompt processing tokens per second separately from generation tokens per second. Then, capture time to first token and total latency, because one headline number can hide the behavior users feel. Run warm-ups before timing. Initial executions may include model loading, memory allocation, or kernel initialization, and measuring those once can swap a subtle 1% runtime change. Repeat enough runs to see variation, then compare medians and spread rather than the luckiest result. Thermal behavior, background activity, and power settings can easily impersonate a tiny optimization. If you build kernels, profile before optimizing. The patch cites hardware timestamps from ropt prof v3, giving the author evidence that this gather was expensive and the rewrite actually reduced its duration. When a benchmark claim appears, ask which operation changed, what share of runtime it consumed, which hardware ran it, and what fallback handles cases where the optimization loses. Local AI gets better, not only through larger models or new chips, but through engineers noticing repeated pointer math, widening a copy, and refusing to regress the awkward cases. So celebrate the 1%, but keep the asterisk. The boring patch is not a universal turbo mode. It is proof that every local token rides on careful, hardware-aware software.